Welcome to the 11th lecture. We're studying upper cutoff frequency, and we started studying upper cutoff frequency in last lecture, where we studied the expression to compute upper cutoff frequency due to input RC network in a BJT amplifier. In this lecture, we will study the upper cutoff frequency, but this would be due to the output RC network in a BJT amplifier. Here I have drawn the same BJT amplifier that we studied in last lecture, with the difference that I have not drawn the input side, right? So I have drawn only the output side of the network, right? We see that this coupling capacitor is no more. Why? Because at higher frequencies this tends to be short circuited, so this won't be there. It will offer least impedance or least capacitive reactance at higher frequencies. But at higher frequencies, we have this total output capacitance that can be computed using Miller's equation. The capacitance that is between base and collector is multiplied by this ratio, and the result is the total output capacitance. We studied this in one of our previous lectures, whereas R out is RC in parallel with RL. And in our last course we have studied that BJT is a current amplifier, and the output current IC is a dependent current source, can be modeled as a dependent current source depending on beta and the input base current IP. So the total resistance that is shown at the output to the AC circuit is this. For AC, this DC tends to be short circuited. So the DC source tends to be short circuited to ground, and we have RC and RL in parallel with each other. And finally, this capacitance, that is the Miller part of the output capacitance of the CPC, base collector capacitance, which appears at the output. Right, now we have this circuit and we have to convert it into a series RC circuit so that we can find out the cutoff frequency. For that, we'll apply the famous source transformation technique. In our earlier courses, we have studied that this can be current source can be converted into a voltage source, and this resistance in parallel with it can be drawn as a resistance in series, and the magnitude of this voltage source is the magnitude of this current source times this resistance. So this comes out to be beta IP multiplied by RC in parallel with RL. And this load is as such. So we have applied source transformation, in which this portion, a current source in parallel with a resistor, is solved so that this network is converted into a voltage source and the same resistor in series. For that, we have to decide the magnitude of this voltage source, and that we obtain by multiplying the magnitude of this current source with this resistor RC in parallel with RL. And the same resistance then comes in series with this voltage source. So this is how we apply superposition theorem. It's a recap from one of our previous courses, namely circuit analysis. So now it becomes a low pass filter. So now it becomes a low pass filter, and we know we have studied that FC upper, at FC, what happens is this XC becomes equal to the resistor in series, RC in parallel with RL. So at FC, these two are equal. So therefore FCU can be written as FCU due to output is written as 1 over 2 pi. We can also write as Rn. Sorry, Rn. It's not Rn, it's R out. R out, C total out. And we know that R out is this RC in parallel with RL, and C out total is CBC times 1 plus AV over AV. Now we have to solve an example in which we will numerically compute the value of FCU given a circuit. And this circuit is the same that we studied in our last lecture to compute FCU due to input RC network. Here we have this. This RC is 2.2K. And RL is also 2.2K. Whereas CBC is given to be 2.4 picofarad, AV is 99, and beta is 125. The same data given in our last lecture, the example we solved in our last lecture. So given this data, given this circuit, we have to find this upper cutoff frequency due to the output network. And before we find FCU upper, we have to find R out and C out total. Computing R out is straightforward. It's simple because we have this RC and this RL. So 2.2K in parallel with 2.2K, it becomes 1.1 kilo ohms. So the first item is simple to compute. The second is also not difficult. The CBC is 2.4 pico. It's given AV. Actually, we computed AV in our last lecture. That came out to be 99. So 99 plus 1 over 99. So it comes out to be 2.4, approximately the same, because this ratio is almost 1. 100 by 99 is almost a 1. So this ratio is a 1. So now we have computed C out and we have computed R out. So now it's time to plug these values in here. So FCU due to output coupling capacitor is 1 over 2 pi. R out is 1.1 K is 2.4 P. P means pico 10 to the minus 12. So solving this gives us FCU upper. So FCU due to output is 60.3 megahertz. So this is the upper cutoff frequency due to output network. Right. Going back to the last lecture in which we computed FCU due to input RC network. And if you go back and see, we computed that to be equal to 1.62 megahertz. Right. So now we have two cutoff frequencies. They both are upper cutoff frequencies, but this one is due to the input RC network, and this one is due to the output RC network. So which one is smaller? This one. So if we draw Bode plot, the portion of Bode plot, this is the mid-band gain. We get first cutoff frequency here, that is the smaller one, FCU due to input. So gains start to roll off at this frequency, beyond this frequency at minus 20 dBs per decade, unless we get FCU due to the output RC network, which is larger. So after this, the gain is the decay is the roll off is faster than it was in this region. So it is like this, and this is at the rate of minus 40 dBs per decade. Minus 40 dBs per decade. So this is in contrary to the lower cutoff frequency FCL, where we had three such numbers computed from three different RC networks, and the gain roll off increased with every new cutoff frequency that we encountered. Firstly, it was minus 20. Then, as we reached the second cutoff frequency, it became minus 40. And then we reached the third cutoff frequency and it became minus 60. But here we have only two numbers. Therefore, initially this is minus 20 dBs per decade. And as we get the other cutoff, the second cutoff frequency, the roll off becomes minus 40 dBs per decade. Right. We will summarize this frequency response in our next lecture. Thank you.